So this is one of our two laws. Law of cosines will come next. That helps us find out parts of triangles. So solving triangles, looking for all of the sides, all of the angles. And so here we have our triangle ABC. ABC, you notice, is not a right triangle. There is no 90 degree in there. Nor do we ever assume that there is a 90 degree. The only time you're going to know there's a 90 is if there's that little box at the corner, or if I tell you, hey, this angle is 90 degrees. Don't ever just assume that it is a 90 degree angle. So, how do we do this? Well, first of all, let's take a look at this H value. Does anyone remember or know what that is actually called? There's a technical name for that H. It's not a hypotenuse. It is the height, but it actually has a fancy name. The altitude. The altitude is the height of a triangle. Now, more importantly, is the fact that how does that altitude connect? That altitude connects to the side across from where it's coming from at a 90 degree angle. Right? So I can draw three altitudes from all three vertices of any given triangle. Sometimes what happens, though, is my altitude has to be drawn outside of my triangle. As in this case, like if I took this length CB and I extended it, pretend that's actually straight, and I wanted to do my altitude from point A, my altitude from point A would actually go out here and connect at 90 degrees. Well, sometimes they're not in the triangle, but they still define the height of the triangle from that particular point. So altitude, new word for you, height of a triangle. So we have this H value, and it's hanging out in there. And if I wanted to find the value of that H, I could use a little right triangle trig. So, for example, let's say we're looking at this triangle. We're going to be doing that triangle right there. If I look at that triangle, that one's a right triangle with this H value, this height, this altitude that's been dropped. And if I'm hanging out at angle C, I can find H by doing a sine. This is assuming that I know this length. If I know that length, this becomes the hypotenuse of that little yellow triangle. And I can say that the sine of C is equal to the opposite side over the hypotenuse side, which in this case just happens to be the variable A. And then if I solve that for H, actually looking for the height, I get this. That's multiply the A, and I get A times the sine of C, and that is now my height, or the altitude of that triangle. And that'll change depending on what angle I'm at. So if I was hanging out at angle A, and I knew angle A, but I also knew the side C, I could say that the sine of angle A is equal to H over C, and then solve for H that way. So you can get three different answers for H just depending on what angle you're hanging out at. Right? So we solve for H. We discover it in terms of a sine. Then we talk about area of a triangle. I hope that we know this already. Did you guys know this formula? Now, we're using K here instead of A to represent area. So area of a triangle, 1/2 base times height. I hope that we already. Why did I say that? Why did I say that? Okay, so the area of a triangle is 1/2 base times height. And all we're going to do is we're going to substitute whatever our H was that we found up here. We go ahead and we stick it in there, and we get this new equation for the area of the triangle. Replace H with, in this case, A sine C, and we get 1/2 BA times the sine of C. All right, following along so far? You guys good? Change some things up here. So this now is our new friend for how I can find the area of a triangle that is not a right triangle. I can only use 1/2 BH if it's a right triangle. it's not a right triangle? Well, now I can use this formula for a non-right triangle and still find its area. That's pretty darn cool. It is. All right, we're almost there. We're almost there. What if I had all of those different areas, A, B, sine C, that's if I knew what the angle of C was, or A, B, sine A, that's if I knew what angle A was, or A, C, sine B, if I knew what angle B was. So if I took all three of those, which are all equivalent, by the way, because they're the same triangle, and then I took it and I divided by this value of 1/2 ABC, you see the 1/2's get to disappear. And in some cases, like if I did it over here, I'll just show you how it works. So the 1/2's get to go away, the A gets to go away, the B gets to go away, and I end up with a sine C over C. And this is the law of sines. So I end up with three different equivalent ratios. Sine of C over C, sine of A over A, sine of B over E. Notice that they're all related. A, B, B, C, C. That's how it'll always set up. And these then become what I use as the law of sines to find a missing either angle on a triangle or perhaps, I don't know, one of the sides. I would need to know the other three components. Like I would need to know two angles and a side or two sides and an angle to be able to use the law of sines. And so that's where this configuration comes in. So there are three different setups that we're going to look at for law of sines. Angle, angle, side. We'll take a look at how that triangle looks. Angle, side, angle. We'll look at that one as well. And then this is the guy that's a little tricky. It's called the ambiguous case. Side, side, angle. What happens now? That's the only one where you could possibly have more than one triangle that results. Oh, all right, so angle, angle, side, side, angle are the configurations that I'm going to need to be able to use the law of sines. Now, you're not going to use all three of these ratios together. You're just going to have two. Either C's and A's working together, or A's and B's, or A's and C's, or B's and C's, something like that. You don't use all three. All right? Can I go to the next page, or should people still writing some stuff now? All right, we're moving. Now, 10 more seconds. Really? All right. Guess you could always. Oh, you could go to the YouTube. All right. All right. Anyway, here we go. We're moving. I'm not writing anything down. You just sit there and eat. All right. So here we have our triangle in an AAS setup. How do we determine what the setup is? Angle, angle, side. I have an angle, and then there's an unknown side between that angle and the other angle that I do know. And then there's a side that I have. So here's what makes this AAS. Angle, don't know side C, another angle, and then a side adjacent to one of those angles. So that's our AAS setup. AAS. Great idea when you guys get these things. Always draw your triangles out. I'm going to be looking for those. Do not be too freaked out about where the A, the B, and the C goes, but do always be freaked out, although you really shouldn't be freaked out. Always know that the angles and their sides are always across from each other. So C is across from C, B is across from B, A is across from B. But it wouldn't have mattered if I called that one B or C. That's not a big deal. These triangles are probably not drawn in any kind of scale, nor are they proportions. So don't, 36 degrees, 48 degrees, they might not look like they're really 36 to 48. Go by the numbers that I'm giving you. Okay, so solving, what does that mean? I'm going to solve the triangle. I want to find all of the missing pieces, all of the missing angles, all of the missing sides. Solving it. In this case, I have two unknown sides, B and C. And I have one unknown angle, angles. Now, one of those is easiest to find without you really having to do any work. Which one? Angle C. And angle C, because I know that all the angles of a triangle add up to 180, I know that angle C would then have to be 180 minus the sum of the two angles that I get. So we can say 180 minus 36 plus 48. And 36 plus 48 is 84. And so 180 minus 84 is 96. Yeah. So there's one of my unknowns. I now know angle C, 96 degrees. So really now what I have is an angle, angle, angle sign. But that's not really important. What's important is the fact that I have the configurations to be able to use law of sines. So here we go. We're going to set it up. We're going to set some proportion equal to another one. Now, law of sines, you can set it up as what you saw, sine of A, sine of B over B. You could also reciprocal that and solve A over sine of A, B over sine of B. The reason I might want to do that is when I'm looking for the sides, put those in the numerator, versus if you're looking for the angles where you leave signs up. So we can write reciprocals. Okay, we're going to look for side B. So I'm going to start with what I don't know. And immediately that tells me what goes below this. If I have B that I am looking for, I'm going to use the sine of B below. So sine of 48 is going to go right there. And now I pick. Now this is the important part. Pick it right. What you have to use next is the relationship in which you have the side and the angle that are known. And that means, in this case, 36 and 8 are across from each other. I have to use that relationship. So I'd say 8 over the sine of 36. And now we're ready to solve for B. How do we get B out of there? Well, you cross multiply. It's the proportion, so you can cross multiply. B times the sine of 36 equals 8 times the sine of 48. Or just take this sine of 48 and multiply it out to the top. So just do that. And you get B is equal to 8 times the sine of 48 all over the sine of 36. So I want to make sure I'm in my right mode with my calculator. And I want to be careful how I put this in the calculator. So do not do this. Do not do sine 48 times 8. Because what your calculator is going to interpret that as is sine of the angle 48 times 8. And that's not what we're looking for. So if you were to punch sine, and then your calculator probably puts a parenthesis, and then you put 48, and then you did times 8, you're doing sine of a 48 times 8 angle, which is a rather large angle. You're actually only taking the sine of 48, close the parenthesis, then you can do times 8. All right, so be careful when you're putting this stuff in. You're going to get some weird numbers if you don't do it right. Who's got it for me? What's the 8, or what's the sine? We get agreement on that? 10.1. Yes? Did we get agreement? Yeah. All right. Good. We now know 2 of our missing parts. We have the angle. We have one of the sides. Now we're going to go find that third side. Now some people might get tempted right here to use Pythagorean's theorem. Why can I not use it? It's not a right triangle. So I can't use Pythagorean theorem. I'm going to have to go use, once again, law of sines. But this time, we're looking for C. So I have to have my relationship of C and its angle equal to a known side and a known angle. Now I have two choices, but I would always recommend using the choice that was given to you. I would always use the 8 and the 36 relationship because those were given to us. We know their exact values. This 10.1 might not be an exact value. So we're going to set it up like this. C over the sine of 96 degrees is equal to 8 over the sine of 36 once again. C then would equal 8 times the sine of 96 all over the sine of 36, and we get 13.5? Yes? All right. So there we are. We have solved all of the unknowns for this triangle using the law of sines. What questions so far? Say that again. Yeah, we're going to have some more. Yeah. Angle C equals 96. Side B equals 10.1. Side C equals 13.5. With all that work. Yep. Okay. I think that would be a lot, yes. Okay, how about another type of triangle? Now we have an ASA setup. Where here I have, in between two angles, I will have a known size. So in this case, you'll notice that I've got the angle and then the side, and the other side or the other angle that would make this ASA is actually the one that's missing. It's this guy. I need to know that angle right there. Yes, Sophia?
Will you always tell us if it's ASA?
I will not. You're going to have to know by looking at the triangle. I will not tell you what kind it is, nor will I tell you what law to use. You're going to have to figure out what law to use based on the triangle. Yes, ma'am?
You know the angle or both.
This one right now is angle, side. We can make it ASA by finding this third angle, A, right?
Yeah.
So if I wanted to find angle A, we do the same thing we did with the last triangle. We say 180 minus 15 plus 120. And then, now we have ASA. So 135, so we get a 45-degree angle at angle A. Now, with that being 45, I have angle, side, angle. And there's the relationship. Okay. Got to find the two missing sides. Which relationship am I going to use to set up my law of sines for this A value? What's my proportion going to look like? Law of sines? I have to. Yes, I have to use law of sines. It's not a right triangle. Can't go find any information other than using law of sines right now. If we knew law of cosines, we need some other information for law of cosines. I don't have enough. But we do know law of sines, so let's set it up for me. Okay, so we take, again, angle and the side, or the side across from it. Those are my relationships. So yes, A over the sine of 45 that one is because what? And these angles and side relationships of 17 and 120 are known. So I will always use one ratio that's a known ratio, and the other one has the missing piece. You plug it in. Making sure I'm putting this into the calculator correctly. What do we get? Do we get agreement on that? 5.7? Yeah? All right, you guys go find V. V over something is equal to, we'll use the same relationship here. And then tell me what you find to be. Fill in what goes in right there. Good. V over the sine of 15, that's what goes right here. You got 13.8 for A?
Yeah.
Uh-oh. Times the sine of 45. Close it. Then divide by the sine of 120. All right, what do we get for B? Come on, people. What is B? You gotta be kidding. What? 5.05? Everyone else get that? Okay, so we'll go to the 10th. All right. So there are two cases that result always in one triangle only. And now we get the tricky part. You guys ready for this? This is good stuff. You're not looking here. All right. So here we go. We're going to do a little break real quick. A little stretch break. All right. A little stretch break. We're going to dive in. We're actually going to try and catch ourselves back up in the calendar. We're going to do, if we can, we're going to try and do 8-1, both cases today. So that's the goal. This next setup, the SSA setup, is the one that we have to pay attention to for the possibility of either no triangles at all, or one or two. So when I have a side given to me, and then there's another side given to me, and then there's just angle, I will have always a situation where one of the sides will have the angle that is related to it, and then I'll have this other side that will be adjacent to the angle, as in this case. So in this triangle we had angle S, which is 40, and across from angle S we knew what its length was. So we knew that that relationship occurs. So there's my sine relationship of a sine of 40 over a 20. And then right next to this angle 40, we had this little R value of 30, creating this side-side angle relationship. Okay, those three components of this triangle are locked in. That angle cannot be anything other than 40. This R value cannot be anything other than 30. The S cannot be anything other than 20. However, the other components of this triangle can adjust. They can be different. Like this angle R can fluctuate, as can this angle T, as can that length T. You can see, you can imagine if I close the angle T, what does it do to the length T? it shortens it. If I open the angle T out, it makes the length T bigger, right? So there's going to be 3 of these components that lock in place, and then 3 that are going to be variable. We're going to be able to adjust. Okay, what makes this so tricky is probably the visual part of this is how do you determine the number of triangles that you're going to get from this situation? Let's just set up log signs for this and let the math convince us of the fact that there's more than one triangle. So how do you do it? Let's set up the log signs. What's it going to look like this? Okay, so we're going to go 20 over the sine of 40 is equal to. Now, Matthew was asking this question earlier. How do you know what to use next? Can I do a TT relationship right now? I have no information about angle T, nor do I have any information about side T. So don't even bother. Do the other relationship where you know you have one component.
The sine of like a theta or something. I mean of R.
We'll use sine of R generically, yeah. So we're going to say that this is equal to 30 over the sine of R. Now here's where I would have taken this relationship and actually written it as a reciprocal because I'm looking for sine values. I will put the sines on top. So I do sine of 40 over 20 is equal to the sine of R over 30. Okay, so up until this point, we haven't had to use sine of R. We have only been finding length. So let's go ahead and find sine of R. Sine of R would equal 30 times the sine of 40 all over 20. Okay, I need somebody to tell me what sine of R is.
How would you put that?
So do 1.5 times the sine of 40. You're in degree mode. These are all in degree mode. Say, sorry? Is it 0? Take me out 3 decimal places. 0.964. 0.964. Okay. Now, here is where we got to go back and remember chapter 6 beginning stuff. Sine values of some angle that produce a positive ratio. How many answers do I have? 2. Where? Quadrant 1 and 2. There's an angle here. We'll call that one angle R1. And then there's an angle over here. We'll call that one angle R2. Because of all support the covers, so I'm going to have 2 places giving me positive sine values. All right. So we go ahead and define these angles. So this is where I consider the possibility of there being more than one triangle. So let's go ahead and find angle R1 by doing the inverse sine of 0.964. What do you guys get here? What am I going to get if I do inverse sine of
74.61.
74 point what?
62.
74.6. We'll go there. Okay, now, how do I find R2 again? How do I do that? 180 minus that. Because 74.6 is a reference angle. Go put your reference angle in quadrant 2 and do 180 minus your reference. So 180 minus 74.6 degrees gives me 105.4 degrees. All right, so here are my 2 angles that could happen for this triangle. There are 2 methods by which I determine the number of answers for a side-side angle situation. I'm going to show you the informal method, and then I will show you the formal method. And you pick which one you want to pick. The informal method I call common sense. It is common sense in this way. You've been given an angle. of 40 degrees. All angles of a triangle have to add up to 180. So if I have a given angle of 40, and I take an angle of 40 and I add that to the two angles that I just found for R, if the sum of those two angles is less than 180, does that mean I have to have a third angle? Yes. All three angles of a triangle have to be 180. So if when I add these together, if they are less than 180, I'll get a triangle for that situation. So 74.6 plus 40, that makes 114.6. Which means I will have an angle T1 of what? What would angle T1 have? What's that? Exactly, whatever makes it 180, which is going to be 65.4 degrees. So T1 would have to be 180 minus that. And that means it's 65.4 degrees. All right, so two angles. Angle R1 produced T1 of 65.4. I created a triangle out of that situation. All right, let's go see what happens with the next one here. So 105 plus 40, that equals 145.4 degrees. Is that angle less than 180?
Yeah.
Yes. So then it will also produce this third angle. We'll call angle T2. And what must angle T2 be? 34.6. Okay. Common sense. That's all I did here to figure out the fact that, oh, I'm going to get two triangles out of this thing. Because that 40-degree angle plus these two angle R's that I found produce a situation where I create these third angles resulting in triangles. Right? So I know that this little scenario here is going to create two triangles, and I know you're asking, how in the world does that create two triangles? Because there's my triangle. You're looking at this triangle and you're seeing that, and you're saying, that's just the triangle. No, it's not. Because we already said that angle R variable, angle T is a variable, so is side T. So here, then, is the visual explanation of why we have two triangles from this thing. So we found our two angles, T1, T2. We found our two angle R's, R1, R2. I have some work to do to go back and find side T1 and side T2. But before we do that, let's see, how did we get two triangles out of this? So here we have our gigantic compass. Now this is actually drawn to a scale. All right? So that 40 angle is actually 40 degrees, and this 30 length is actually a scale, 30 length, and this 20 length is actually a scale. Notice that I drew the 20, though, as this dashed line, because that's the swinging part of the compass. This is the angle that's fluctuating, angle T. We said that that's a variable angle. S is locked in place, 30 is locked in place, 20 length is locked in place. But angle R and angle T and length T down here on the bottom, they are going to be different. So you can physically see the arc that resulted when I swung the compass, or didn't swing the compass, I actually moved the compass along that arc. See what results from that. Okay, there's the arc that results from that. How many places did that arc touch that horizontal line? It touched it in two places. One of the places it touched was right about there. And then, as it swung a little further to the right, it ended up touching, right about there. So when it hit the first time, right there, it created angle R1. And angle R1 we just found was 74.6 degrees, because inverse sine of 0.96. And then it swung a little further to the right, and it created angle R2. And angle R2 had an angle of 105.4 degrees. So I get two triangles that result from this particular situation. Now each of those triangles now looks like this. And now we can physically see the length of T's. T1 down here is longer because angle T1, 65.4 degrees, is bigger than what we had for angle T2, which was 36. So I get a longer length down here. So this one was 74.6. Then we got 105.4. And I think this was 30, what was it again? 34.6. And then 34.6 degrees, and creates that triangle. And you can see that angle T2, which is smaller, produces a smaller length T2. So does that help in seeing how we get two triangles out of this situation? To physically see the actual swinging of the arc? Okay, all right. Thank you for your input. Now, explain to me, how would this situation result in no triangles? What would have to be different? Okay, so I heard Christy says if it was more than 180, what is the it you were referring to? Okay, if the angles that I added up happen to be more than 180, I don't get a triangle. Right? In the drawing right here, what would I adjust so that this thing, when it swung from that point, doesn't hit the side? What would I have to do? Shorten. If I shorten it, so let's say this length wasn't 20. Let's say it was 15. So if we take this guy and I shorten the length of the compass, and now we swing an arc, I don't ever intersect that side down there. So if that given side is too small, there's no triangle that results. All right? What would describe a situation where there is going to be only one triangle? Thinking a bit, again, how do I adjust this compass? What would the compass have to look like this time so that I just get one triangle out of it?
You would have to hit the x-axis.
At what kind of an angle? A 90-degree angle. So if I took this length now, and I stretched it out just long enough, I need to keep stretching out a little bit further. Just a little further. And okay, a little further. Oh, look at that, right there. So if I was swinging an arc there, what are you laughing at? All my screw up. Yeah, we're not worried about it. But you can see, if I did that, I had a situation where I was able to intersect exactly at a 90-degree angle one time. It's called, you're connecting tangentially. Then I have a right triangle. Only one. So only one triangle results from this case. There is another time, though, when you get only one triangle. What do you think would be different now? There's another time where this happens, where I get one triangle. When it's way bigger. Right, so what if we took this thing and we stretched it out even further? Oh, maybe not that much. Maybe like that. Look at this. Now when I swing over here, I miss the right side of the line, but I don't miss the left side of the line. So now I actually get a triangle that looks like this. Oh, hello. Fancy. Alright, so I get that big triangle, only one, and there are my two cases where I can get one. So there is only one opportunity to get two triangles, when the length is just right that I cross it twice. There are two places where I get one triangle, once when I just hit tangentially to the line, and the other, why are you laughing? It's not a funny word. It's a word, tangentially. And then, yes it is. It is a damn word. Look it up, tangentially. Name your kid tangentially. Right. And the other one is when my arc is so big that it intersects on the left-hand side, but misses on the right. So those are the what I would call the common sense ways of knowing how many triangles I have for the ambiguous case. There is a formal way, but we'll have to look at that in just a second. We have to actually go back and finish this. Because we didn't find little t1 and little t2. I got to find all the parts of this triangle. So real quick, let's find little t1. So there's my triangle that resolves. How am I going to find little t1? Showing all of that stuff right there. Yeah, I'm going to the sine thingy. There it is, the sine thingy. All right, so I'm going to set up law of sines. T1 over sine of 65. Enthusiasm is killing me. And then 20 over the sine of 40. And there's little t1. So somebody knock that out for me. That's little t1. T1. What are those? Got it for me? Almost.
Halfway there.
Halfway there.
I got 28.29.
28.29. Do we get confirmation? 28.3. All right. And we would do the same thing for little t2. And then there's my information for all of these triangles. So in your homework, some of your homework is going to ask you for how many triangles can you get? And that's where you have to do either this common sense approach. Never find your given angle and then add it to whatever your angles are that you find for R1 in this case. We use what we use, R1 or R2. Here is your formal way of doing it. So the formal way, method 1. We'll call it method 1. I told you we're going to try and squeeze it all in and get it done. Trying to get ourselves caught back up. Ambiguous. Now you only do this when you have that side-to-side angle. You don't set it up the other way. Okay, so make note of the triangle and how it is currently set up. Where side A, side B, side C is. Because I'm using that setup of that triangle to reference the ABs and the A, sine A things in this method 1 scenario. Alright, so with that information, look at this. And imagine here, with what I'm showing you, imagine, get the picture in your head of the compass we just did. In our first scenario, where A, there it is less than B sine A. So we're talking about it's smaller than this length right here. Then if it's smaller than that length, I'm not going to ever intersect that horizontal side, the horizontal bottom, BA length of that triangle, which means no triangles exist. So if you can identify, we're hanging out at this angle, by the way, and we're using these two sides. So if you can identify those parts, then you just plug them into these little rules and figure out how many triangles you're going to get. The second scenario, what if our A happens to be the same length as this H value? That's the case where I get a right triangle connection, 90 degrees. In the third case, where I have the little a is in between B and B sine A, that's the case where we swung and we intersected twice, we get two triangles. Wake up. And then finally, the last case, if that A is way bigger than that length of B, then we said that's the situation where I only intersect one time. So that's the formal method. You wanted to use that. And then the method that we used, I called it method 2, but also called it the informal, is this one. So here's just the written description of what we talked about, of how we came to discover that there were zero, I just say go back and look at this. Of how we came up with the fact that there were two triangles. So take a look at this later on YouTube or on Blackboard notes. But that's just what we described using that compass. That's the process we use to determine how many triangles there are. All right? So with our last bit, you guys hang in there. You're good. Here we have this. And we're going to find out what length B is. And a little different in the sense that I'm giving you cosine of A, I'm giving you cosine of an angle, and I'm giving you sine or cosine of B. So in order to answer your question, Sam, I've given you enough information to have that kind of a setup. Okay? In an angle side angle situation, I would have to have in between two given sides, I would have to be given an angle. And in this triangle, the way that it is currently set up, I do not have that. If I had an angle side angle situation, I would have to know that side X and this angle B to have an angle side angle. Angle side B and A would have to be known, and side X would have to be known in order to have angle side angle. For angle side, I would have to have something that looks kind of like this setup. Angle A would be known, angle B would be known, and 6.
So they're not like right next to it.
And then if I had a side angle, I need to see another side on here. And I don't have that, so it makes sense. All right, so how can we find this B in simplified radical form? We've been dealing with law of sines, which means I'd love to be able to set up law of sines. I'd love to be able to do this. Sine A over 6 is equal to sine B over B, because that's what we are looking for. But the problem is we don't have sine stuff. We have cosine stuff. So I'm taking you back in time. How do we convert those cosine and sine things into, or cosine values into sines? How can we do this? This is a little tricky. Let me have my blackboard again. How do I do that? Make it a sine value. Multiply by a tangent. Okay. There's a couple different things you could do. Going way back to the chapter 6 beginning, I have a cosine of an angle producing a 1/2 ratio. 1, 2. What does the other side have to be? Root 3. It has to be a root 3. So now can I say what the sine of A is? Sine A is root 3 over 2. Oh, hey, look at that. Cosine of a b equals negative 1/4. Where does that have to happen? This has to happen in quadrant 2 or 3, but we know it's not going to be in 3 because I can't have angles that are bigger than 180 in a triangle. So I've got this set up where I have x over r, which means I got to find that. How do I do that? Anyone have any ideas on that one? How do we find that y side? Pythagorean identity. The Pythagorean theorem. 16 squared minus 1 squared. So 4 squared, sorry. 4 squared minus 1 squared. 16 minus 1 is 15, and this would be equal to the square root of 15. And therefore, sine of b would equal square root of 15 over 4. All right, now I have everything I need. I have sine of a, sine of b. I can plug those into our law of sines equation. Except we're not plugging an angle in. We're actually physically plugging the value of sine of a and the sine of b. So sine of a is going to get replaced by a root 3 over a 2. And then I'm going to divide that by a 6. And sine of b is going to get replaced by a root 15 over a 4. And then that's going to be divided by b. So I can go find out what b is. Setting up my proportions. Got a little work to do on that one, huh? So we have root 3 over 2b is equal to root 15 over 4 times 6. Root 15 over 4 times 6 times the reciprocal of root 3 over 2. And I'll let you guys go ahead and finish it from there. You can do the simplifying and the rationalizing and stuff, but that's how we can find little b as an exact value, simplified radical form. We didn't have to make it in decimal, just from using our trig setup. So no ambiguous case there, just using law of sines. So nothing